Thank you. So so I will give 3 talks. The first one will be on standard nudging and also asymptotic observers, because the nudging method is known as an asymptotic observer in automatics. And then tomorrow I will speak about optimal nudging, and on Monday on a new nudging scheme, which is the back and forth nudging. So for today I will present first the nudging scheme. Then we will study a little bit the linear case, in which the nudging scheme is known as the Luenberger observer. Then in the nonlinear case, we will see that it's possible to derive some observer also, and I will show an example on the Lorenz model. And then, more complicated, the shallow water model, and I will show that we can also design some observer for data assimilation. So I think that now you all know very well data assimilation. So the goal is to retrieve the state of the system from the knowledge of, on one side, some model equations, and on the other side, some observations. The main problem is that the fluids are very turbulent, sometimes chaotic, and then it's very difficult to identify precisely the initial condition or the state of the system at a given time. And so the idea is to use data assimilation to combine all the information that we have to try to find the best possible estimation in order to have the best possible forecast. So a small scheme. So you can summarize data assimilation probably with that. You have the model. If you know some initial condition and sometimes some model parameters, then you can integrate in time and compute the trajectory in the future. And you have also observations which are discrete in time and space. They are also noisy usually. And the goal is to find the best possible solution of the model, and best possible is as close as possible to the observations. So this, from mathematical point of view, is a typical inverse problem, because if you know, well, the goal is to retrieve the system state from sparse and noisy observations. So the direct problem is, if you know the good solution, you can extract observations, and the inverse problem is from the observations, get back to the solution. So first, the nudging. So I consider a very simple model because it's dx over dt equal f of x, but almost any geophysical model can be written like that. So it could be partial derivatives here, and in f of x you have everything, all the spatial differential terms. So you can write that. You can even Navier-Stokes equations or so on can be written like that. And I assume that there is no unknown model parameters at that time. So from an initial condition, you can integrate this model from time 0 to capital T, and you get a solution. Then you have some observations. So we assume that here we assume that they are sparse in time and space. Sometimes we will assume that they are a continuous solution. We assume that we may assume that they are noisy, and we may assume that they are not physically related to the model state. So in this case, we need an observation operator, so I call it H, and it allows to compare the observation with the model solution. Okay, so usually there are two parts in the observation operator. First, some interpolation or extrapolation, because you have two different grades in your numerical model, one for the model and one for the observations. Okay, the satellite, for instance, will not observe exactly where your model, where you have the model solution. And also you have a change of physical variables, because still the satellite may not observe exactly your model variables. Okay, for instance, your model variables may be the temperature, the velocity, and so on. And satellites will observe some radiances that can be related to the sea surface temperature or height or things like that. I like this picture because there is an Airbus A380, and I was in Toulouse a few years ago. So you have a different source of information. Yesterday we had a talk about the buoys and what the people were doing with that. And most of the observations come from satellites, geostationary or polar orbiting, and they can be sensitive to the clouds, and they observe radiances, so you have to use some simple models to get back to the model variables. So what is nudging? So you have your model like that, and the idea is very simple. You add a feedback term to the observations directly in the model equations. So you have some observation, y-ups. You have the model state, x. You apply the observation operator so that you can compare h of x with the observations. And this term, you multiply it by a gain matrix or a nudging matrix, or it can be the Kalman matrix also in Kalman filters. And the idea is that this feedback will make the solution X converge or get closer to the observations. Okay, it's like minus kx. If you remove the observation operator, you have minus kx, so you just nudge to the observations. So it is probably the first four-dimensional data assimilation scheme. It has been used in the 70s and 80s and 90s. It's less used now because people prefer to use 4D-var or Kalman filters. But sometimes inside the 4D-var scheme you have some nudging to improve the 4D-var. So the idea is that you use dynamical relaxation to adjust the solution towards the observations or towards something else. It could be towards the analysis of a Kalman filter, for instance. So it's very inexpensive, as you have seen, because you assume, of course, that you have a model and that you have observations, and then you can add this inside the model code, even if this is a kind of black box, very complicated. You can, it's very easy to add at each time step. Once you have computed the solution of the model, at the next time step, you can add the nudging term. So it's very easy. It's inexpensive because there is almost no cost to add this term. The main problem is that people say that it's you need a heuristic, and it may not be physical to add this term, this relaxation term. We will see that it's wrong. The main idea is that with the nudging, you add small, maybe continuous data corrections, whereas in Kalman filters, or optimal interpolation, 3D VAR, you have large and intermittent data corrections. It is common that in Kalman filters, for instance, when you make the correction step, you may have a shock in the solution because you add a term which is not very small, and it can be located at some points of the model, and then you may have gravity waves or things like that. Whereas in the nudging, if you, for instance, interpolate your observations, we will see that you add only small and continuous corrections. So there is no shock, and it's more physical. The solution, the computed solution is more physical. So what happens if you have discrete observations? Because you cannot just add a small correction at the exact time and location of your observation. So in time, usually the same observation is used over several time steps. So you can use this kind of interpolation. So if the observation is at this time, you add the correction at these 3 time steps. Or you can add or use a Gaussian to have something very smooth. And in space, the observation is also spread to a local neighborhood of the observation. For instance, still using Gaussian, you can use different radius of influence for the different observations. And at the end, what you add, the correction, the nudging term is very smooth in time and space. And you use it as several time steps and several breakpoints. So a few references about nudging. So probably the first application to a real meteorological problem is from these two guys, Auroux and Lorenz. At the time it was a 1D shallow water model, but it was in the 70s. So then it has been used in a quasi-geostrophic ocean model in the late 80s and 90s. Then for mesoscale atmospheric ocean atmospheric model in 90. And then people try to do some, let's say, mathematics on the nudging scheme with the optimal nudging. So several people worked on the optimal determination of the nudging coefficients. And then the team of Enrico worked on sensitivity studies. So from that paper, he concluded that nudging is not good, it's not physical, and people should not use it. But then some people are still using it, hopefully. So first, let's give a variational interpretation. So we are back to the model equation with the nudging term here. If we use an implicit discretization of this equation, so we assume that at time n or tn the state is xn, at time n plus 1 it's xn plus 1, so the derivative in time is simply replaced by xn plus 1 minus xn over delta t, and then here everything except maybe the observation, but it could be n plus 1, is implicit. Then xn plus 1, the solution at the next time step that you want to compute is solution of the following equation. So it's the same, I just multiply by delta t, and x is the unknown. So let's take a particular nudging matrix, which is H transpose R minus 1. So R is the covariance matrix of observation errors. So it's, you have seen it already in, for DIFR Kalman filters. Because we compare the model solution with the observation, so we have to use weight, and this one seems to be the best one. And then you need something to get back from the observation space to the model space, the state space. So H transpose is also the best choice. So if you use this particular gain matrix, yeah.
Time n, we are considering the observation. Yeah. So why are you going for the variable at n plus 1?
We assume that we know the solution, the state x at time n, and we want to compute the solution at time n plus 1. Okay, we want to solve this
but
model.
We want to make the variable towards the observation.
Yes.
If we are considering observations at time n, we would like to bring the model output at time n closer to the observation.
Yeah, but also at time n plus 1. At every time.
Suppose the model is like,
What's that mean?
we are getting a model output at suppose time n.
Yeah.
We are having an observation at that time n. We are using a nudging technique to nudge or bring that observation, model variable towards that observation.
Mm-hmm. Okay, I assume there is n plus 1 here.
Then that's what I'm saying. Suppose
Yeah.
if you're writing that xn minus xn minus 1, would be
Yeah.
better?
Okay, so the best is to put xn plus 1 here. This is a mistake. Okay, so you would like xn plus 1 to be close to yn plus 1. But then here we are working not at observation times, but it's the time steps, so it's very short time, so you can always...
Time window here.
So here the delta t is very small, much smaller than the observation times. So you can put n or n plus 1, there will be no difference in practice because you have some observation here, and then you have your time steps here. So whether you consider xn or xn plus 1, both should be close to the observations. But it should be n plus 1 here. Okay, I will correct it.
And you said you're only doing that for a few steps.
Well, here I assume that there is some available observation. If there is no observation close to the time step n, then there is nothing here. Or I assume that I have observations at any time. So we can write the same equation with H transpose R minus 1. We assume that the model is derived from an energy principle. So for instance, you can think that the heat equation so the model, if you remove the diffusion coefficient, the model is simply the Laplacian operator. And then we will see that this comes from an energy. So the idea is that the solution x of this equation is the same as the minimum of this variational formulation. So here you have the energy of the system, the scalar product between fx and x with a minus. So for instance, if f is the Laplacian, then minus Laplacian x dot x is simply the square norm of the gradient of x. So this is the standard energy for the heat equation. So here it's the same. If f is a physical model, then usually minus fx dot x is the energy of the system. And this is the quadratic distance to the observations. It's the same term as in the 4D VAR. So the idea is that the next, the solution that you compute at the next time step with the nudging is exactly the minimum of the compromise between the energy of the system and the distance to the observations. So I think that it is at least as physical as the 4D VAR, in which you minimize the compromise between the observations and feedback to the background state. So we will see tomorrow and Monday that it's possible also to compare nudging with Kalman filters, of course, because it has the same shape. You have the nudging matrix K, which could be a Kalman matrix, times the distance to the observations.
So it seems that nudging is much easier to implement.
Yeah, much more.
Go from 3D VAR to 4D VAR instead of going to nudging. 3D VAR to nudging.
So why people did?
Operationally, why was 4D VAR, so to say,
Because several things. First, the nudging we will see is as an asymptotic convergence. So you need a quite long time to get the solution close to the observations. So for operational windows, 6 hours, for instance, in weather forecast, it's probably not enough. And maybe people didn't look at this scheme from the mathematical point of view to see how it works. And whereas the 4D VAR mainly comes from mathematicians. And then people knew how it worked, and then people were able to use it, probably things like that. And then we can say that the 4D VAR can also identify model parameters, model error, and things like that. So probably nudging is too simple. So in both nudging and Kalman filters, we can see that the model solution is corrected with the innovation vector, which is the difference between the observation and the corresponding state. So we will see tomorrow that if the nudging matrices are set in an optimal way, in some optimal way, then we find the standard Kalman filter. Generally, it's more a suboptimal Kalman filter. And we will see also on Monday that we can iterate the nudging in a small time window in order to improve the convergence of the solution towards the observations. So, first, we studied a linear case in which we can do some things, some mathematical things, and try to understand how it works. So everything is linear, so F, the model is supposed to be linear, so it's a matrix. You can imagine F is a matrix, and X is a vector. And we assume also that H, the observation operator, is linear. The standard nudging is the same, dx over dt equal f of fx, and then we add the nudging from the feedback to the observations. So let's assume that the observations are extracted from a reference solution, a true solution. Okay, we assume that the true state is known. Of course, it's never the case, but anyway. So we assume that the model is perfect also. And we have a solution of the model X true with the true initial condition. So if we know everything about X true, then there is nothing to do. Okay? So we assume that we know X true through the observation operator. So we know the observation, which is H times X true. Okay, so remember that H is a matrix, but it's not a square matrix. Okay, from X2 that could be a huge vector, dimension 1 billion, for instance. The observation can be only 1 million points. So you know a very little part of the true solution. So the nudging term, the nudging equation is there. And if you replace the observation by H x true, you see that the nudging state is the solution of this equation. Ah, it's probably the... Okay, so I stay there. So we will take the difference between these two equations. Okay? And look at the error between x true and the nudging state x. So the difference between dx over dt and dx true over dt is this part. So this is the equation of x, and this part, which is the equation of x true. And we can rewrite like that. So f times x minus x true, and kh x true minus x, sorry. So at the end, the error E is solution of dE over dt is equal to f minus kh E. So everything is in this matrix, f minus kh. So the model minus the nudging correction. So probably the first guy that studied that was Luenberger in the 60s. And the idea is that if this matrix is a Hurwitz matrix, so namely the spectrum, all the eigenvalues are strictly negative, or their real part are strictly negative, then E goes to 0 when time goes to infinity. And then it means that the nudging state converges towards the true state when time goes to infinity.
So the only thing that is wrong about the nudging state is the initial condition?
Yeah. So the solution of this equation is the exponential of the matrix times t. And if you imagine this is a diagonal matrix or simply a coefficient, if it is strictly negative, then we have an exponential decrease of E of t with time. Okay? And the decay rate is something like the largest eigenvalue of this matrix, which is strictly negative. So the point is that it's asymptotic in time. So if you work with a fixed time window, then the decrease may not be very important. So let's take a very simple example. So there is an ODE in dimension 2 with this model matrix. Okay, X has two components, and the derivative of x1 is simply x1 plus x2, and the derivative of x2 is also x1 plus x2. So we can see that the eigenvalues of this matrix are 0 and 2. So 0 is the difference. If you take the difference x1 minus x2, it's constant. And the eigenvalue 2 is the same, x1 plus x2. So we assume that only the first component of x is observed. So we take this particular observation operator. Okay, from x1, x2, you extract only x1. And then we are looking for a gain matrix, which has this shape, two components, it's a 2 by 1 matrix, such that f minus kh has two strictly negative eigenvalues. Okay, because f has two positive eigenvalues, so if you use the wrong initial condition, for sure the trajectory will not remain close to the true solution. Okay, it will diverge exponentially in time. So f minus kh is this, 1 minus k1, 1 minus k2, 1 and 1. And the characteristic polynomial is this one. And we can see that, for instance, if we choose k1 equal to 4 and k2 equal to 5, then, so here you have 2 and here you have 1, and then you get lambda plus 1 square. So the two eigenvalues are minus 1 and minus 1. So the matrix is stable. And so everything should work. The nudging system is stable, and then you can use any initial condition. You should converge towards the true solution. And in this case, as the two eigenvalues are minus 1 and minus 1, the error decreases asymptotically in time with exponential minus t. Yeah?
So, I mean, in filter, common filtering and so on, K, I mean, the gain matrix is somehow determined by the variational problem. That's not true. You've got this freedom to choose the gain.
Yes. But we will see that, well, we have the freedom to choose in order to get close to the observations. Sometimes it's not the good idea to be close to the observations if you have observation noise.
But your variational formulation doesn't force a particular nudging matrix K.
No. Here we use the particular nudging matrix here, this one. But we may use any matrix K such that the system is stable.
How you are getting this?
Because I wrote this, and I saw that it would be nice to have H transpose, so that it's the derivative of this term. And then if I add R minus 1, I get exactly to the 4dvar term.
So is there an equivalent variational formulation for a general K? I guess there is.
Well, you need a H transpose at least, but probably it's the only operator that you have from the observation space back to the state space. So you can put any matrix here instead of R minus 1, as long as it is a positive definite matrix, probably.
Yeah, you are using two objects.
Yeah. After? Backward?
Another one.
No. Forward or backward? Next?
Forward.
Back to what you were doing.
Yeah, here I'm using true observations, yeah.
So how you are getting this observation has no error.
Yeah, but it's a theoretical study. It's only a theoretical study to understand how it works. We will see that in numerical experiments you can add some noise on the observations, and then, so here you have plus some noise, and then we will see that you will not converge towards the observations, but towards something close to the observations, and that's the model. The model will remove or filter the noise, and you are still.
If we add noise here, these are basically synchronization.
If you add noise here, then you have some term here plus some k times the noise, and then here you still have plus something. So it's not enough to have strictly negative eigenvalues to have the error going to 0, because you have a forcing term coming from the noise. But then you know that the error E, you can control it and ensure that you will have E smaller than something. You can make the error decrease, but it will not decrease to 0 if you add some noise. But you can control the norm of E with this term, if you assume that the noise is not too large.
Is there any effect on one
Now if there is some noise, then the solution X will not converge to the true solution, but it will be close to the true solution. But then there is no influence on K. You can use the same K, and it will work also. It will not converge to exactly the true solution, but then the more if you have a large noise on the observations, then you should use a smaller K, because the observations, you cannot trust the observations, so you should not have a large feedback to the observations. But for reasonable noise, the K can be the same as if there is no noise. Okay, so the the numerical test. So here I plot only x2, because I assume that I observe x1, so I know x1, and there is no noise on x1. So x1 is known. x2 is not observed, and I start with the same point for x1, but not for x2. Okay, the true solution is x1 0 is 1, and x2 0 is -2. So as the sum is negative, then all solutions are going are decreasing. And then I start with a wrong initial condition, which is 1, 0, where the sum is positive, and then if there is no nudging, the solution is going to plus infinity, because the eigenvalues are 0 and 2, so the sum is amplified by an exponential. So here the sum is positive, so it's amplified, and the sum is negative, it's amplified in the same way, but in the negative part. So if there is no nudging, x2 is going to, sorry, x1, so I'm wrong here, so you have to switch, because x1 is observed and x2 is plot, so you have to exchange the two values here. So if there is no nudging, the solution is going like that. Then if we use these two coefficients, k1 and k2, for the nudging matrix, in this particular case, the eigenvalues of f minus kh are 0 and 0. So the error remains more or less constant between the two solutions. Then, if we increase k1 and k2, now the eigenvalues are -1 and -1, and the solution will converge to the true state exponentially in time with the rate exponential of -1. If you increase, take for instance these two values, the eigenvalues of k minus f minus kh will be -2, and so it will go faster. So you can see maybe that this one is getting closer to the blue. So I could have plot for a longer time. Maybe we'll do it Tuesday in the hands-on lab, so you will see. So I should add convergence. I could have plotted the decrease of the error in time so that you can see that the decrease is exactly -1 and -2. And you can increase k1 and k2, and then the solution will get closer and faster to the true solution. So, what are the conditions of existence of a stable gain matrix K? Because for any model F and any observation operator H, you cannot assume that it will be possible to stabilize the model. Okay? So, the idea is that the system is observable if given two solutions x1 and x2 of the model, if the observations that you have hx1 and hx2 are equal, then x1 is equal to x2. Same initial condition and then same solution. Okay? So the observability condition is simply that if you see the same thing for two solutions, then they are equal. You don't miss anything. Or simply the system is observable if the initial state and then all the solution can be obtained from only the observations. So by linearity, H and F are linear. The system is observable if and only if the solution, so the solution at time t is exponential of ft x naught, and then you observe it, so you have h exponential ft x naught. You make the difference x, here is the difference between x1 and x2. So if this observation is equal to 0 at any time, then the initial condition has to be 0. It cannot be something else than 0. This is the observability condition. This is equivalent to the fact that there is the kernel of this matrix is simply 0. So H, and then at the first time step you apply the model F and you observe, then you apply again the model F and you observe, and so on, n times, well, n minus 1 times. And then at the end, you have a sufficient condition for the observability of the system. So the system is the model F and the observation operator H, which is that the rank of this matrix is exactly n. Okay, you take the observation operator H, H times the model, H times the model times the model, and so on until H times n minus 1 times F. Okay, you apply the model n minus 1 times, and then you observe. So there is a result which is known as the pole placement or pole assignment method that says that if, still in the linear case, if a system FH is observable, then there exists a matrix K such that F minus KH is stable. So all eigenvalues have a strictly negative real part. So in this case, it is possible to find a nudging matrix K that makes the nudging work, and you have the nudging state converge to the observations, to the true state. The problem is that usually it's difficult to compute this matrix, okay? You have an existence result, but it may not give the construction of the matrix K. But you know that you can make it. In this case, it's easy to compute H and F and HF, sorry. And, so we will see if the observation condition is satisfied. So H is 1, 0. HF is 1, 1. Okay, you compute this matrix, and you can see that the rank is 2. So the observability condition is satisfied. So there exists K. Okay, so let's move to the nonlinear case.
The existence, is that a unique one or a
No, there is no uniqueness. Okay, so nonlinear case. Can we build some observer or nudging term for nonlinear models? So we start with some particular nonlinear system with a linear part, F, and a nonlinear part, G. And we assume that G is... it will not work probably because the rank is not H transpose H has the same rank as the size of H, and it will be difficult to control all the eigenvalues of F with a very... Well, if H is a very particular matrix, like in this case, sorry, here, with 1 and zeros, then H transpose H will be a very partial diagonal matrix, so you control only the eigenvalues corresponding to the observation locations. So it might not be enough. But you can try, maybe. Okay, so we assume that G, the nonlinear part of the model, is differentiable in Lipschitz. So it means that G of x1 minus G of x2 is smaller than L x1 minus x2 for a given positive Lipschitz constant. Or it can use an equivalent definition with the derivative of G, which is bounded by L. So we still assume that the system is observed like that. You observe the true state through the observation operator H, and we assume that Fh is observable, only the linear part. Then we know that we can stabilize F. We know that we can find K such that F minus Kh is stable. And the idea is that G, the variation of G is not very large because you can control it with L, and probably if you know how to stabilize F minus Kh, you know how to stabilize F minus Kh plus L, let's say. So we introduce the following nudging term. It's the same. We add the nudging matrix times the observation minus Hx. So the observation comes from the true state. So this is the standard nudging term, standard Luenberger observer. So if we look at the difference between x and x true, then we find, so this term comes from x, and this term comes from x true, linear, non-linear terms. So the difference, so the equation d over dt is f minus khe, so the linear part, and then you have a new term which is g of x minus g of x true. And the idea is that this term is smaller than L times x minus x true because g is Lipschitz. So it's some sense smaller than L times E. So if we look at the square norm of E, so we simply multiply the previous equation by E, and 1/2. So 1/2 of the derivative of the square norm of E is E times d over dt. So it's this. This part is smaller than the largest eigenvalue of f minus kh, or the real part, times the square norm of E. And this is smaller than the norm of E times the norm of gx minus gx true, which is smaller than L times the norm of E. So at the end, the square norm of the error is controlled by, the variation is controlled by lambda max plus L times the square norm of E. With the identity, because L is a scalar, so you simply shift the model from L times the identity. it will still remain observable, so you can still control it, and so you can still find k such that f switched by L minus kh is stable. So you can control everything here and make the nudging state x converge to x true. Sorry? The second inequality here should be? Why should there be the size of the matrix?
Oh, sorry, okay.
No, because the norm is the sum of all the vectors. So in this particular case, with the nonlinear part, which is Lipschitz, you can still control it and make the nudging work. So a simple example, the Lorenz system with no t. And I use the standard values of the parameters sigma, rho, and beta, such that you have the standard chaotic behavior with the butterfly shape. So this model can be decomposed like that, where x is the vector with the three variables x, y, z. F, the linear part is this, and the nonlinear part is 0 minus xz and xy. So this is not Lipschitz in general, but if we assume that the trajectories are bounded, so if you simply look at that, you can imagine that if you start with initial conditions that are bounded, then the solution will remain bounded. And in this case, the function g is Lipschitz. So if you compare to g of x, you will find after something, so everything is bounded by 2 or 4 times the bound of the solutions times the square norm of the difference between the two solutions. So it is a Lipschitz function as long as the solutions are bounded. Okay, here, these terms here are bounded because the trajectory is bounded, and then these differences here are bounded by the square norm of x2 minus x1. So for some L, which is maybe 4 times the bound of the trajectories, G is Lipschitz. So we should be able to make it. So we define this Luenberger observer, the standard one, and we assume that we observe x and z, but not y. So in this case, h times f is this vector, and h f square is this one. And you can use MATLAB, for instance, because it's a 3 by 3 matrix, so it's a little bit difficult by hand, but if you have time, you can do it. I use MATLAB to check that the matrix H, HF, HF square is a full rank matrix. And in this case, then, the couple FH is observable. And then we can place the poles of F. We can stabilize F, find K such that F minus KH is stable. I think that if you observe Y and Z, it's also the case. If you observe only X and Y, it will not be the case because F has a particular structure, which is you have the block 2 by 2 here, and then this coefficient. So there is no coupling between X, Y, and Z. So you need at least Z and X or Y. So if you observe only X or Y, the system is not observable. The matrix will be from 2 only and not 3. But you can still stabilize the matrix in this case. Okay, there is no theoretical result that says that you can do it, but you can do it. So let's try with h equal to 1, 0, 0. That means that you observe only x. And then if you take this gain matrix K, then F minus KH is this matrix. Okay, you just remove this row here. And then you have three negative eigenvalues. Minus 1, minus beta, and minus sigma. So it is a stable matrix. So it should work.
Your decomposition into linear plus nonlinear is what you need.
Well,
Linearized at some other point.
it's unique in some sense because I just removed the nonlinear part and I took. Well,
Zero in some sense at the origin.
yeah, I could add any linear part in the nonlinear term, but I simply cut linear terms and
I see what you did.
yeah, you can decompose. Yeah, as long as G will be Lipschitz. Yeah, the decomposition is not unique. I took the simplest one, but
The theorem that you said applies only for the linear system, right?
yeah.
Because you said there is only finite condition.
Mm-hmm.
So because of the nonlinearity, even though it is not observable,
No,
it's able to connect there.
no, it's not observable because of this particular choice of H. I only look at the linear part here. If you just take the linear part, so you remove xz and xy, this system is not observable if you observe only x. It means that you can find two different solutions for which you have exactly the same x. So if you look only at x, you may miss something because y and z can be different things. Okay, you can have two different solutions with the same x solution. Okay. So if you observe only x, you cannot identify the solution because there are many solutions that have the same first component x. So it's not. Yeah, it's possible, but there is nothing that tells you that it's possible. There is no result that says you can do it. But in this particular case, by hand, you can see that you can do it. But for sure, if you observe x and z, for example, you know that you can make it. If you observe only x, theoretically you miss something. But as there is a nonlinear part, then in fact you don't miss anything and you can identify the solution. If you remove the nonlinear part, if you observe only x, for sure you cannot make it. You can find two different solutions with different y and z with the same x. So you can miss something if you observe only x. But here in this case you have a nonlinear part, so this will help to identify y and z. So I will show you on this example. I try with another solution. So you can try with this one, H and K, and it works. But we can try with something else. So let's define this observer. We assume that X is observed, not Y, not Z. So X is observed, but you don't put anything on X. Okay, no nudging down on X. Then Y, you replace X by X true in the equation of Y. And you also replace X by X true in the equation of Z. Okay, so this is the same equation as the standard Lorenz system, in which you replace X by X true in Y and Z. So we can rewrite this system like that so that you can see the original Lorenz model. And here in red, you have the previous nudging term that we found just before here, the one that makes f minus kh stable. And then I add these two blue terms, which are also nudging terms, but not constant in time. It's not a constant times x true minus x. Now k depends on y and z. So it's a k of t. It depends on the time. And it depends on the solution that you are considering. Okay? So we use this k. No, because you're looking at the difference between this equation and the true state. And minus z would be -1 on the third row and second column because it's the equation of y. So if we look at the eigenvalues of f minus kh minus s, we get this characteristic polynomial. So minus sigma is still eigenvalue. And there are two more eigenvalues. Beta is positive, and the idea is that you have x true square. So whatever x true is, the two roots of this polynomial are negative, or of real part, of negative real part. So you have three strictly negative eigenvalues, whatever x true is, and then the error will decrease asymptotically in time. Okay, so you can check the sign of the eigenvalues because the sum of the two eigenvalues is -1 minus beta, and the product is beta plus x true square. So let's try. The true state is initialized with the initial condition 5, -5, and -4. And the nudging state is initialized with -5, 5, and 4, so the opposite. And we assume that only x is observed, the first component. And here it should be, so it's x. So the true state is in blue. And then we start with -5. So if there is no nudging, you have the green curve. So you can see that if there is no nudging, it's completely wrong. If you add the nudging term, then you have the red curve, and you can see that you converge towards the blue curve. And it's the same for y and z. The red curve goes towards the blue curve asymptotically in time. And you can see that if there is no nudging, then it's completely wrong. So here you have the decrease of the error, the difference between the true state and the nudging state as a function of time. And it's in log scale. And you can see the decrease with the slope is nearly 1, -1, which corresponds to the largest eigenvalue. Okay, in the matrix, the eigenvalues were -1, minus sigma, minus beta, I think, and the largest one is -1. So of course it's nonlinear, so the eigenvalues depends on x true, so it depends on time, but the largest one is close to -1. Okay, so now let's move to the shallow water model. So we consider here a very simple 2D shallow water model. So there is no Coriolis force, there is no wind stress, there is nothing, almost nothing. So we assume that we are in a square domain with rigid boundaries, no slip conditions on the boundary. And so it's 2D. H is the height, the water height, and V is the velocity. So it has two components. So this is very simple equations. They are derived from Navier-Stokes equations, in which you remove the vertical part. You assume that the vertical scale is very small, so you keep only the horizontal scale. And at the end, you keep only the conservation of mass and momentum. So for instance, the height of the water is simply transported by the velocity. And the velocity is transported, and it depends on the pressure gradient. Okay, if you have a variation of the height, then it will increase or decrease the velocity. So we assume that the water height h is observed. And the question is, can we identify everything? Can we retrieve the velocity of the fluid? Can we define an observer that corrects both variables? So you can imagine that for ocean problems, the height could be observed pretty well with the satellites, but not the velocity. Okay, velocity observations usually come from ships and floats and things like that, so not much observations compared to the satellite observations. So the idea is that we take this equation, the shallow water model, and we add some nudging term, and we can imagine that we had one term, a scalar function for h and a vectorial function for v. These functions will depend on, of course, v and h, and what is observed, h, the observation of h. And then there are several assumptions. The first one is that if h is exactly the observation, then you should not correct anything, because you have the correct height, so you cannot do anything. So these terms should vanish when h is equal to h ups. And then we will use some requirements here. The first one is a very physical one. The model has some symmetries. The shallow water model is invariant by rotation and translation. Okay, you can put your huge swimming pool or ocean wherever you want on the Earth. It will be the same behavior. Okay, you can rotate the ocean, translate the ocean, it will be the same. So these terms should be invariant by translation and rotation. Then we will use some convolution smoothing inside F, because we will see that the observations can be noisy, and you have to smooth the observations. And particularly if we differentiate the observations. And we need local stability, at least. It means that the linear system has a strong convergence. So if you linearize the system, the observer converge strongly to the true state. So, the idea is that it's a very nice result that says that if you look at differential operators, differential in space, if you take only invariant operators by translation and rotation, then the only one that is left is the Laplacian. It's the only operator that is invariant by rotation and translation. So your functions, your merging terms will be functions of the Laplacian. You can use polynomials of Laplacians. Also, the dependence of V should be the norm of V, or the square norm of V. You cannot use only one component of V because it will not be invariant by rotation. And also, H, the dependence, will be H minus the observation, because it has to go to 0 when this term is equal to 0. So at the end, you find some polynomials of the Laplacian, the observations, the square norm of V, and H minus the observations. And also, if you want to use V, then you have to take another polynomial, take the gradient and the scalar product with V. And the vectorial counterpart for the correction on V, is another polynomial of the same things times V, and the gradient of it, and there is no V here, sorry. So you may imagine a lot of functions that at that time. Now you need to add some smoothing by convolution. Why? Because if there is a Laplacian of the observations, for instance, the observations are noisy, and if you take a nudging, if you have a noisy signal and then you take the derivative, you have something extremely noisy, and if you take a second time derivative, it's even worse. So you need to smooth this term, and the best choice is a convolution by some kernel. The kernel has to be invariant also by translation rotation. And at the end, so it's simply a convolution of the previous polynomial times kernel that depends on the square norm of the variable. So now, let's take the most simple one among all these polynomials and functions. The most simple one is no derivatives, because even if you smooth the observations, taking the Laplacian of it is too noisy. Okay, so there is no, only the constant term, so no Laplacian. And so now you take the smallest order possible among all the terms, and at the end you simply have the convolution between the kernel and the difference between the height and the observed height. And for the velocity, the simplest one is the convolution of kernel by the gradient of h minus the observations. The most simple invariant kernels is the Gaussian. Take the exponential of minus x squared minus y squared. And the same for the other one. And what you know is that this observer is symmetry preserving. You have a convolution with the Gaussian, so it should be relatively smooth. So it should be robust to noise, and the high frequencies are completely filtered by this. Oh, we will see.
Okay.
Fine. Now you can take any alpha and beta. Yeah.
What was the question? How do you choose alpha?
Ah.
What sort of width of your filter?
So if you take alpha very large, this will be simply a direct function, okay, simply at the origin. So this will be simply the nudging, standard nudging. At a given point, you only correct with h minus h observed at this point. Okay, and if you take a smaller value, then you have a small Gaussian. So let's study the convergence on the linearized system. So it's a linearization around the equilibrium state. So the height is constant and the velocity is equal to 0. Okay, nothing happens there's nobody in the swimming pool. So the linearized system is here. Delta H is simply linearly transported by delta V, and delta V is simply given by the gradient of delta H times the gravity constant. And then the estimation errors are given by that. And the idea is that you can eliminate V from the unknowns and find a second order equation only on H. So the estimation error on H is given by this equation. So you can see the two convolution kernels. And so it's a wave equation. Second derivative in time equals second derivative in space. And you have, and it's a damped wave equation with the viscous damping. And thanks to the viscous term, we will see that this solution will converge to 0. So there is a result. If you take these kernels with strictly positive constant, then the system is strongly asymptotically convergent. And if you use, if you look at the H1 norm of the height plus the L2 norm of the derivative of the height, then it goes strongly to 0. So it means that you have a strong and asymptotic convergence of H, of the error and the height, and then also on the velocity. If you are back to this equation, you can see that if H goes to 0, if the gradient of H goes to 0, then V will also go to 0. So the observer, the nudging state, converges to the true state when time goes to infinity. And you have an exponential decrease of the error, and it's based, the proof is based on Fourier decomposition of the solution, and the rate of convergence depends on the coefficients that you use here. So some numerical experiments. So here it's the decrease of the estimation error on the three variables, the height and the two components of the velocity as a function of time. So it's a log scale. And we have these values of alpha and beta. And at the beginning, the initial condition was totally wrong, because I took, I think, 0 for the initial condition of the nudging state. And you can see the decrease is almost constant. The decay rate is almost constant for the three variables. Okay, only H is observed, but then we can find also Vx and Vy. So if you have discrete observations, so first we can imagine that the height is available everywhere, but not every time. So then, let's say that there is no more theoretical study, it's no more valid, but then we can still do some numerical experiments. So if we assume that the height is available only every 12 time steps, so we add the nudging correction every 12 time steps, the estimation error still decreases like that, but the convergence rate is nearly 12 times smaller than in the previous case. So in practice it's 11.7, and it's quite nice to see that it still works, and it's there is almost no difference between continuous and discrete observations. At that time there is no noise on the observations, but we will see that when there is noise, if you don't put the convolution kernel, the results are not very good.
Yeah, but so the previous theorem talks about the noisy case.
Here, no, here you can simply take a very large value for alpha and beta equal to 1, and then there is no convolution. It's simply a Dirac function, so there is no convolution.
Then I can say that. And
then it's still true. So, but it works also with the kernel convolution. Okay, so discrete observation in time do not degrade the scheme. So it's quite nice. So here we add some noise on the observations. So there is at the end nearly 20% of noise on the observations. And we do the same. We start with a completely wrong initial condition. And we look at the convergence for the three variables. And it's the same, except that you have convergence nearly at 1% of error. So this is quite nice because if you know the height with 20% noise, you can always filter the noise and get H with good precision. But what is interesting is that usually if you only correct H with the observations, and if you don't correct the velocity, the error on the velocity would be 20, 30, 40% at least. Here, you control the velocity with the gradient of the difference between the height and the observed height, and then you're able to identify the velocity with also less than 1% error. So this is very new. And then, as I said before, we can compare with standard nudging if we take very large values of the alpha coefficient, such that the Gaussian is close to a Dirac function, and then there is no convolution. You simply correct at the location where you have the observation. And then the estimation error is nearly 3 times larger with the standard nudging than if you take Gaussian with a radius close to 1, let's say. Okay, so so we can see that we have seen in the previous slide that all the variables are identified with less than 1%. Standard nudging is simply you remove the convolution. At the location where you have the observations, you add H minus H ups. And it's 3 times better if you add the convolution with the Gaussian with a radius of the order of 1. I tried with 1/2, 2, there is no big difference. Sorry, here. So let's try it with the nonlinear model. Now it's a nonlinear shallow water model, and it's even worse than the model I presented at the beginning, because here it's a geophysical model with Coriolis force, with wind stress, with many things. And I use the same nudging term, observer term, with the same convolution kernel. Still 20% noise on the observations. And you can see the decrease of the error for the 3 variables. So now the height is estimated with nearly 2% of errors, and the velocity it's 20 to 30% of error, which is quite small for geophysical shallow water model. If you use the convolution kernel, then you get a better solution, nearly 1.5 smaller error than with the standard nudging if there is no convolution. And so here, if you look at the height, so I choose 3 different points in the domain. They are located near the main current of the shallow water model. And you can see the variation of the height versus time at these 3 points. So you don't see the third one, but so in black you have the true state. In blue, the identified state. And in green, the observations. So there is a small mistake when I made this figure, because in the code the observations are not, I didn't store the observations but the noise, and when I made the figure I added the noise to the identified state instead of the true state. So the green points should be around the black one and not the blue one. So you can see that it's not a Gaussian noise. Okay, it's a uniform distribution. So it's not the best choice when you use Gaussian terms. And you can see that even if you have this information in green, you are able to find the blue one, which is close to the black one. And for the velocity, it's almost the same. You can control the velocity with these green things. And you can see that if you take the derivative in time of the green points, it's not a very nice thing.
Good question. I don't know if you played with this, but I'm interested if you turn off your nudging once you found it. How did this go? Yeah, so if you got to, say, the middle, turn it off. I mean, I guess it's kind of effectively off anyway. Sure.
On the height, it's not very fast, but on the velocity, it goes wrong very fast.
Really?
Yeah. Because if you don't control the velocity, it's quite bad. Because you have as long as you have some difference on the height, you have some difference. Where's the model? This term will make the velocity wrong. Yeah. The height is more stable. Okay, so time for a conclusion. Nudging is very simple. If you take a shallow water model, quite realistic 2D shallow water model, it will take you maybe half an hour or 1 hour to add nudging, maybe a few days for a Kalman filter, and maybe a few months for 4D VAR. So it's probably the simplest 4-dimensional data assimilation scheme that you can use. You can make a continuous forcing of the model with the observations, which is quite interesting. The nice thing also is that the model is a weak constraint, because you don't assume the model to be perfect, because you almost never solve the model exactly. You always have the nudging term in addition to the model. So you are not looking for a solution of the model. So that's a good point if the model is wrong. There is a physical interpretation of the nudging with the variational principle, and we will see there is a link with also the Kalman filters. And many people, mostly in the automatics community, are working on observer design for nonlinear PDEs. So it's quite new because for several years they studied only ODEs, and then they had nonlinear terms, and very recently they started to design observers for PDEs. So the next steps is to try to work on a full primitive ocean model. Okay, more or less the full Navier-Stokes equations. The question is the same. If you observe, for instance, the sea surface height, can you control and correct the non-observed variables? And how? So it's related to this point. Can we design some observer for a full primitive ocean model? So this has been done in a very particular context. For the US Army, in at least in the Iraq War, they used nudging as a real-time data assimilation for weather forecast to predict if there will be some wind. And so I know that they used that. They were able to put everything in a Hummer with a small satellite antenna, and they get the observations from the National Center, and then they compute something during 15 minutes, and then they get the weather forecast for the next hours. So it's probably not possible to do 4D VAR in real time, because you need several hours to get the forecast for many days. And then try to get some theoretical convergence results for nonlinear PDEs, which is quite difficult, but it should be possible for simple nonlinear PDEs. Okay, that's it.
Theoretically, suppose you observe velocity, h is easy to control?
Yes, I think so. Probably because it's linear in, if you know V, it's linear in H, so I think it's not very difficult. So I didn't try because it's not common to observe the velocity, but
Easier to measure, let's say, right? Then easier to measure. No. This model, yes, but I am more worried about the structure of the equation. Anyway,
yeah, I think it's easier. Okay, so time for lunch.